I think there are many paths to a high performing language models. So right now there's a proven strategy. People follow that. I think that doesn't have to necessarily be the only path. I think my prior is that as long as your model architecture is reasonable and is hardware efficient and you have lots of compute and you have lots of data, the model would just do well.
Hey there, I'm your host, Kan Jun, and we are Generally Intelligent, an independent research lab developing AI agents that mirror the fundamentals of human-like intelligence and that can learn to safely solve problems in the real world. On our podcast, we interview researchers about their behind-the-scenes ideas, opinions, and intuitions that are hard to share in papers and talks. We hope you learn as much as we have in our quest to understand and build the mind. Tri Dao is a PhD student at Stanford, co-advised by Stefano, Ermon, and Chris Ray. He'll be joining Princeton as an assistant professor next year. He works at the intersection of machine learning and systems, currently focused on efficient training and long-range context. Well, we're really excited to have you today, Tri. Thank you for joining us. We use a lot of your work, and we're really excited about talking today. And we'd love to hear, actually, how did you get into research? And how did you develop your initial research interests in the beginning?
Yeah, thanks, Kanchan and Josh. I'm really excited to be here. I work in the area of machine learning and systems, but actually I started out being more on the machine learning side, specifically more on the theory side. My background was in math. I did my bachelor in math, and I took classes in machine learning and convex optimization. And that's when I fell in love with machine learning, because it's a combination of what I love, machine learning and math and computer science. So I got interested in doing research. I started out doing research with Stephen Boyd in convex optimization at Stanford. That's why I knew I wanted to do research. And my PhD, I started out doing much more on the theory side, simply because that was what I was interested in. So we studied questions that are a little bit more, I would say, abstract and somewhat removed from applications. So things like characterizing what kind of matrices would have theoretically fast multiplication algorithm. And I did that for a couple of years. And then in 2018, 2019 or so, I think when we found a bunch of really interesting results on the theory side, we wanted to apply these results in practice. And that's when I realized that we were missing a bunch of ideas on the system side. So as an example, we have these matrices that theoretically have fast multiplication algorithm, but when you implement them on, and you run them on GPUs, that's when I realized that, hey, these fast algorithms in practice can run much, much slower than kind of a dumb multiplication algorithm that now GPUs are really optimized for. So something like for matrix, n by n weight matrix, and you multiply by a vector, usually the algorithm takes on the order of n square runtime. So that's kind of the naive algorithm. We were developing algorithms for a specialized matrix that take on the order of n log n, log n, log square, and things like that we thought from a theory side would be much more efficient. And then, I spent a couple of weeks trying to implement them as efficiently as possible on PyTorch. And I realized that unless for most values of n, our algorithms is actually much slower in walk log 10. That was very surprising to me. Now, I tried really hard. Of course, for really large values of n, the kind of asymptotic started to kick in and our specialized algorithm get faster. That's when I started to realize that, hey, if we want to make these things useful in practice, we need more ideas. And that's when I started to think more about how these algorithms actually map to the systems they run on, be it CPU, GPU, or a distributed training setup. And I started talking to systems folks. And that's when I learned a bunch of new things on the system side. There are a bunch of tricks that folks on the system side have been thinking about for decades, right? They understand that, these accelerators like GPUs have special matrix multiply units. They have different levels of memory hierarchy that you need to block and tile differently to kind of make them friendly to the hardware. That's when I learned a bunch of new things about the systems that these algorithms run on. And I realized that it's much more useful for me to think about algorithms as well as the hardware. So more recently, I've been designing algorithms that take advantage of hardware. So things like hardware-aware algorithms take advantage of how they have specialized matrix multiply units, while they're like block-oriented devices. So they want to do like a bunch of things in parallel, or they have different levels of memory hierarchy that we can take advantage of. And in the past couple of years, we've seen quite a bit more success in terms of putting these things in practice. So there's a lot more to be done in this area. And of course, it's a very exciting time where training large models is now the norm, and these models bring a lot of value. So I'm really excited about the future in this direction at the intersection of machine learning and systems.
That's cool. Do you think it's well known in the optimization field that you started out in that these algorithms actually like often run slower and need to be much more specialized for hardware? Like, are other people also doing that, or is it this is not really a known thing?
I think it is known to a subset of folks who actually put these things in use. So there are folks who prove theorems more on the theory side, and to them, they're just solving a much more kind of abstract mathematical question of what is the optimal number of floating point operations that we need to do. And those are extremely interesting questions, and I benefit greatly from reading the theory side as well. But there are some folks who actually put these things in practice in building systems, and they don't do anything. Once you come into contact with actually building anything that someone else is going to use, you start to have to think about hardware. Now, how deep you go depends on how much time you have, how important it is. Sometimes you might favor a more maybe mathematically elegant approach, even though it's like 5 to 10 times slower, because that's okay. Sometimes the purpose is like, hey, we have a nice simple thing that's mathematically elegant, rather than, hey, we have this maybe slightly more complicated thing that's 5 to 10 times faster that someone will readily use. So I think it depends on the focus. Nowadays, I think it's especially in the last couple of years where large models, like large language models, train on massive amount of data, I think the importance of engineering, of thinking about hardware is now much more widely used. Going forward, I think more people will be interested in this area. More tools are being developed to make it easier to reason about the hardware, to take advantage of hardware. So I think going forward, like more and more people will be using ideas from both hardware and algorithms to build these new models.
That makes sense. Cool. Zooming back to you were 2018, 2019, when you were starting to realize these hardware things. Let's talk about some of the work that you did at that time. In 2019, you had a paper out, which is a little less directly what we were talking about on the system side, but theory of modern data augmentation. I thought was pretty interesting. How did that paper come about? Like, where did your ideas come from, and what was the kind of the core idea?
We were thinking about kind of a more data-centric approach to understanding machine learning models. So for a while, people focus on what the models do, how are they designed, and so on. And there's still a lot of that going on, and we definitely think about it that way too. One inspiration we had was that there's more of a shift towards understanding what the models are doing by looking at the data that they are trained on. Because back then, I think 2018, 2019, we saw a lot of computer vision models that improved their accuracy mostly by augmenting data. Like clever data augmentation schemes seem to give much better results. Or like, you can improve like ImageNet classification accuracy by 3 points, compared to if you tweak the model in this one way or the other, you can get like 0.5% improvement. We saw that the improvement is mostly coming from data augmentation. So let's try and go and understand what's really going on. So we want to understand what people have been doing in practice and kind of shine a more theoretical light into why that works. And we borrowed theory from the kernel methods kind of literature. So that was all the rage back in 2012 or before 2012 or so, where most of machine learning people were focusing on kernel methods. And of course, there's still a lot of nice mathematical framework there. So we use some of the framework there to explain what happens when you augment the data and how that changes the features that the model can learn. It's part of a larger trend of not just looking at the model design, but also looking at the data that the models are trained on. And I think nowadays, for example, for large language models, there's now quite a bit of data engineering work involved as well. And people are realizing that, hey, it's really important to curate the right data set if we want to control the model behavior.
That's right. How would you describe kind of your understanding, either from that paper or since then, about what is going on with data augmentation? What did the kernel theory tell you about data augmentation?
I think data augmentation is one way you can encode knowledge into the model. So in computer vision, you might have knowledge that, hey, images should be, if you're classifying an image, then the identity of the object and the image shouldn't really change if, let's say, you blur the image a little bit or rotate them a little bit. And you have that kind of knowledge and you want to encode that knowledge into the model. So one way you can do that is by encoding special layers into the model that maybe take average of different rotations or something, explicitly doing some kind of pooling. And people have done that. These are called equivariant networks, and they can work well in some cases. The simpler way to encode this kind of knowledge into the model is just directly modifying the data. And people have found that to be a little bit easier to reason about. It's a little bit more intuitive. And so far, that approach has been a little bit more popular. I think taking that in the modern setting, maybe in the last couple of years or so, where people are using data augmentation to do contrastive learning of models, which the idea just says that, hey, let's say we don't have labels for the images, but we know that if we rotate the image a little bit or transform the image a little bit, we want the representation to be around the same compared to a different image. So that is taking the same idea, which is encoding whatever knowledge that we have into the data instead of directly into the model. And that approach has worked really well. So CLIP is a really good example where just by contrastive learning, the model is able to, with unsupervised data, so no label, the model is able to learn really good representation and do good zero-shot object classification.
Right.
What we found was that there is a mathematical link between data augmentation, which is changing the images, and kind of feature regularization, which is changing what kind of features the model should learn. And mathematically, we do a first order approximation and say, hey, approximately what the model is going to learn is some kind of average feature of different images. Let's say if you're going to rotate the images a little bit, it's almost equivalent to taking average of the rotated features. And so that's one way you can understand what data augmentation is doing, which is somewhat equivalent to enforcing some kind of invariance in the features that the model will learn. So this is helpful in things like robustness and so on. It's also helpful if you want to, let's say, instead of having to augment lots of data, what if we then want to translate whatever knowledge we have about images into, instead of manipulating images, we can also manipulate features, which are less intuitive, but we have this nice mathematical link between the two. So I think that's one helpful way to understand data augmentation.
Oh, that's really interesting. Got it. And so creating a mathematical link between the data augmentation and the feature representation is kind of the important thing here.
Right. Yeah.
And outside of vision, like, now thinking about transform models that are more recent, is there anything that breaks in this link, or does it still feel interesting?
Right. Yeah. So I think text is a little bit harder to understand what's really going on in terms of data augmentation for two reasons. One is that the text data is discrete. So for images, you can rotate things a little bit and say that's the same image or almost the same image. For text, it's a little bit harder to do. The input space is discrete. And two, there hasn't been that many text augmentation methods. There's been some, maybe generating synonyms and swap out synonyms and things like that. But that hasn't been really that popular. People have just been focusing more on, hey, let's just collect more and more text data from very diverse domains, Wikipedia articles, web text, code, and so on. And that has proven to be easier to do or more effective rather than focusing on figuring out how to augment text data. I think the direction is still going to be let's just collect as much text data as possible, because that tends to be the limiting factor for the model performance nowadays. And we've seen lots and lots of great work coming out, how to collect more text data, how to curate data, how to deduplicate data, and so on.
Mm-hmm. That makes sense. Going from when you were there in 2019 and thinking about how you made it to starting to think about some of these like butterfly factorizations or kaleidoscope, like how did you initially get to these ideas? And
I guess what was that first paper that you mentioned earlier where it was like, I started implementing this thing and then it actually turned out to not be useful.
Yes. Yeah, that butterfly line of work actually started the very first paper that we wrote, the butterfly factorization HTML 2019, was actually done in like 10 days or so, because we had a much more ambitious goal that I was trying to do in the preceding 6 months or so. So we saw that earlier we were studying different classes of matrices that have fast multiplication algorithm. So that's more on the, let's say, numerical linear algebra side of the world. And if we put our machine learning hats on, we want to say, hey, can we learn these things from data? Can we learn algorithms directly from data? Similar to how someone would discover, let's say, the fast Fourier transform algorithm, let's say maybe Gauss discovered in the 19th century or Cooley and Tukey discovered in the 1960s, can machines automatically discover these algorithms? That was a much more ambitious goal. So we were trying out ways, let's say, given inputs and outputs of some transform. Let's take the Fourier transform. If someone gives you the input of a Fourier transform and output of Fourier transform, can you figure out a fast algorithm to turn the input into output? So can machine automatically discover these algorithms? Back then, I thought it was a crazy idea, but we gave that a shot, and it didn't work. It works well for small dimensions. So we were able to make it work for matrices of size up to, I think, 16 by 16, something like that. The idea is to find a parameterization that can contain a lot of these fast transforms, and then you can learn over the set of parameters. And the problem we ran into was that there is this kind of combinatorial aspect of searching over different algorithms. For example, at each step, you might choose to combine, input element number 0 with input element number 7 or 8 or 9 or 10. There are so many choices. And so when you compose them, you kind of have an exponential number of choices that you have to make. So if you want to kind of learn these transforms from data, then you have to learn over a very, very large discrete set. So that was a really difficult problem. We made some progress for small cases. And then towards the end, we decided that, hey, what if we make the problem simpler? What if we fix some of the structure and learn some of the other structure? So that we decided, hey, let's just fix the kind of matrix structure and only learn the magnitudes of the entry. And that turned out to be the butterfly factorization, again, borrowing directly from the fast Fourier transform. We fixed the structure, let's just learn the magnitude. And that turned out to work pretty well. We made the problem simpler. And in 10 days, we run experiments, wrote the paper, and it turned out better than I would have expected, given that we essentially had 10 days to do it. Of course, afterwards, we went back and kind of cleaned up a bunch of things, and we solved a bunch of problems that we couldn't solve before. So there's been a long line of work on these butterfly factorization then. But back then, we started with a much more ambitious goal. We didn't quite get there, but we found something pretty nice, which is these butterfly factorization. They've been around for a while, but we finally made them work. And then since then, we've understood things quite a lot more, and we've had a lot of follow-up work building on butterfly factorization.
Can you talk a little more about some of that follow-up work, like pixelated butterfly? Obviously, I think probably came from that. Are there other papers that came from that?
Right. Yeah. So the first paper, we just wanted to understand if we can learn the algorithms from the data. And we showed that we can learn a bunch of different algorithms like fast Fourier transform, Hadamard transform, and so on. And then the next step is, how do we apply this in a machine learning setting, training, let's say, image classification models or speech recognition models? We found that, surprisingly, if you compose a bunch of these butterfly matrices, they can represent any fast transform, essentially. We prove a really nice theorem is more on the theory side, which says that any transform or any matrix with a fast multiplication algorithm can be written as product of these butterfly matrices, up to some log factor something. But the gist of it is that we found a universal representation for these fast transforms, right? That you can compose products of butterfly matrices and you can represent any fast transform. And so when we put that into model training, so we parameterize the weight matrices. So normally these weight matrices, such as dense matrix that you learn over, instead we replace them with products of butterfly matrices. And they have certain nice inductive biases, like for audio, because they can represent things like Fourier transforms, they're quite well suited for audio, for example. So that was the paper we had called Kaleidoscope. That's more on the expressivity side. So we figured out that, hey, we can use these things to represent lots and lots of transforms. One thing we ran into was that they're still not hardware efficient. Even though theoretically, again, they're like, n log n or n log square n, things like that. The actual implementation isn't as fast as just an n squared multiplication algorithm for many cases, let's say on GPUs. And so more recently, we've been thinking about how to make these things hardware efficient. And we came up with a nice parameterization we call Monarch. Monarch is a kind of butterfly where instead of these butterfly factors, we can group a bunch of them into essentially block diagonal matrices up to some permutation. And because they block diagonal, we can leverage really efficient implementation of matrix multiplied. That works well on GPU. And that has made things quite a bit faster. So Monarch matrices are 3 to 5 times faster to multiply on GPUs compared to the old butterfly parameterization, even though they take more floating point operations and they take more parameters. So surprisingly, you increase the number of floating point operations, but things goes faster because we are able to parameterize them in a hardware-friendly way.
Yeah, that's interesting. So I imagine Monarch came from some work prior on sparsification or on trying to figure out, okay, well, it seems like making them block sparse is better.
Right.
You get to this block sparsity idea.
Yeah. So I think that's around the time when we start to understand or dig a little bit deeper into hardware. One way to understand butterfly matrices is that they're a product of sparse factors. And sparsity has been a pretty old idea, right? Lots of people have been working on that since the 60s. Jan LeCun was working on sparse CNN since the 90s. In signal processing and in optimization, sparsity has been an important idea. So lots of people have been trying to make sparsity work. There's a large literature on things like pruning, lottery ticket hypothesis, and they're all very, very interesting. What we wanted to do was that we wanted to make them actually hardware efficient so that we can train with sparsity. That has been difficult for a lot of people simply because the hardware that we use, GPUs, are very much block-oriented devices. So they prefer a kind of dense parallel computation rather than sparse computation. And so we wanted to make the sparsity work, and we realized that to make them work for GPUs, we need to impose some kind of block structure so that there's still enough kind of parallel work going on so that the GPUs can be efficient. So we have a paper, Josh mentioned, Pixelated Butterfly, that uses block sparsity with some of the butterfly idea. And that could work pretty well for training things like transformer. But that did some approximation to the butterfly factorization. So it wasn't, in terms of expressiveness, we had to sacrifice a little bit to gain in hardware efficiency. And after that paper, we thought a little bit more, and then we found this nice parameterization called Monarch that we didn't have to sacrifice expressiveness. So it can represent anything that perhaps butterfly matrices can represent. At the same time, it remains hardware efficient. So that was something that we were after for a long time.
What would you say has been kind of the impact of that? What was the result from that final paper? And what was the impact, do you think, from that work? Yeah.
So I think we finally found some parameterization that involves, sparsity that's expressive and hardware efficient. And so we were able to use that to train image classification models, let's say on ImageNet, that gives actual walk clock speed up while maintaining the same level of quality. In language model, we were able to use that as an intermediate step to train language model with sparsity for 80% of the time and then transition to dense for 20% of the time. So we do get speed up from sparsity while maintaining kind of the quality of the dense model. And now these things are being used at Salmonova, which is a chip company. And lots of works are now building on kind of the idea of sparse training. So for example, the folks at Cerebras, they released their own kind of GPT model that used sparsity throughout training. So we've seen that sparsity, I think now is proved to be more useful as people think about sparsity, hardware-friendly sparsity. So I would say the high-level point is we show that, hey, there are ways to make sparsity hardware-friendly. There are ways to maintain quality while using sparsity. And since then, I think lots of folks are building on these ideas and make things work for different applications.
Is Monarch widely used? And if not, why is it not more widely used? I've always been quite puzzled by this.
Any method would have certain applications in mind. So for sure, we found that it can work pretty well for image classification models. But for a language model, for large data sets, we needed something more. Because our intuition was that for language models trained on large data set, you need lots and lots of parameters to do well. That's been kind of the scaling law. And we observed that empirically as well. And so if you replace these dense weight matrices with something that's sparse or something that's like Monarch, you reduce the number of parameters. And they would not do as well. So that's why we had an experiment where we trained with sparse for 80% of the time. And then with the last 20% of the time, we transitioned to dense matrices to close the gap in terms of quality. So in some applications, we do see that it works well. For some applications, we do see that we need something a little bit more. So our intuition is that for applications that can leverage, fast transform, where fast transform is kind of the right inductive bias, like in audio or in images where things like convolution work well, then Monarch could work pretty well. For other applications where there's not a lot of structure, essentially you just need a lot of parameters, like language model, then you need something more than just Monarch matrices. And we show one way. It's always like a proof of concept. Hey, here's an interesting idea. Let's see how other people are building on that. So it is being used at a few companies that I mentioned, but like any method, it has certain strengths and weaknesses.
So basically the inductive bias, you think, from the block sparsity and like this particular setup for language models is not quite right. And so you have to go back to the larger, denser matrices at some point anyway. And so it's maybe you're not buying a lot in this case by having this extra complexity.
Right. And I think more recently, the folks at Cerebras kind of figure out a way to use sparsity throughout training as well. And of course, it's tailored to their hardware, where it's a different kind of structure. I think it's like 1 out of 4 elements, adjacent elements are non-zero, something like that, is well suited for their hardware. And so they can make it work, using sparsity throughout training. There's still a lot of work to be done. I know NVIDIA has 2-4 sparsity for every 4 adjacent elements, 2 of them can be non-zero, things like that. That hasn't seen massive adoption, but I think in certain cases, like language model inference, I know lots of folks are thinking about using that kind of sparsity.
I see. Interesting.
But not necessarily for training. For training, right. It feels like that's not quite the right inductive bias.
Yeah, I think for training, people have been a little more conservative. For language model training, we know that there's one formula that works. You collect lots of data, you train a large transformer model, and that has worked really well. And so people, for the application, they just want a good pre-trained model, and that's a proven strategy to do so. And then whatever they do is going to be on the kind of post-training or fine-tuning stage. And so that's where you have a little bit more flexibility to experiment with. Whereas for the pre-training, it's going to take a month on hundreds of GPUs. So you don't want to experiment too much there.
Yeah, that makes sense.
Yeah.
Well, we'll run those experiments.
Yeah. I guess, have you heard from any other of the larger labs like Google or Anthropic or OpenAI about them kind of exploring any of these things? Or do you think that they're also sort of just sticking with the kind of tried and true way of doing it?
Mm-hmm. I think in large organizations, there are definitely folks more on the research side. So they're more willing to try ideas that are kind of off the beaten path. But there are also folks more on the production side where they can be reasonably confident that it's going to work, like 80 to 90% that's going to work. So I think that more researchy folks will be willing to try more things. I think Google has been pushing for mixture of experts, which is a different kind of sparsity that's also hardware friendly. I know the group led by Quirkla has been working on that for several years. They have some of the models that seem to work well, but we haven't seen anything public yet. So there's still lots of work to be done. People are thinking of hardware sparsity as one way to get essentially more compute out of the GPUs we currently have or the TPUs we currently have. So it's definitely an exciting area in the future.
You mentioned that people are looking into using this kind of sparsity for inference. How would you use it for inference?
Right. I think there are a couple of ways you can speed up inference. Let's say if we focus on just large language model inference, which is what a lot of people are thinking about these days, then there are a couple of methods. Quantization. Instead of using 16 bits, you can use 8 bits or 4 bits, and that can work pretty well. You can use sparsity, where you can zero out some of the entries in the weight matrix. We have some of that work coming out later this year, but there's already been work on using sparsity to speed up model inference. So there's Sparse GPT, I think is the name of the paper, where they show, hey, you can zero out like 50% of the entries of the weight matrices, so you reduce the amount of memory required by 2x and things like that. These approaches are emerging, and people are definitely paying attention. Maybe they're not kind of widely deployed yet, but I think they will be in the future.
Mhm. If you were kind of intuitively thinking about large transform models trained on language, intuitively, like what is your perspective on each of these methods, like quantization versus zeroing things out versus something like Sparse GPT?
Yeah. So I think these are complementary. So I would say there are maybe three main approaches. One is quantization. Lots of work is being done there. The focus there, my understanding is that has been to reduce the amount of memory required to run the model at all. So this is great for people running on consumer GPUs. They only have, I don't know, 8 GB or 16 GB of GPU memory. If we quantize the model, that can fit into their local GPU. So for example, Tim Detmers and collaborators has done a lot of fantastic work in this area. And folks have shown that, hey, you can quantize and kind of preserve the quality of the model. I think in terms of speed, I haven't seen as much positive experience on quantization as we would expect. I think follow-up work is going to try and speed these things up using quantization. Right now, maybe there's a little bit of overhead of quantization that they're not as fast as they can be, but I think follow-up work will address this limitation. So quantization, I would say, right now it seems to work in terms of quality, in terms of speed. We've seen some work in this direction already, and we'll probably see more work in this direction, making quantization actually fast. For sparsity, we've seen some work showing that, hey, we can preserve quality by zeroing out. If we zero out like 50% of the entries, in terms of speed, I would say I haven't seen as much work on how to speed up walk clock, how to reduce latency with sparsity. We have some of that work coming out later this year. The last class of approach is like modifying the model architecture to be a lot friendlier to inference. So the first two approaches, I would say, they don't want to change the model architecture. They assume that, hey, we already have a pre-trained model, let's say Llama or something, and we can either quantize or sparsify and so on. The third approach is like, hey, let's think about inference during training as well. Can we change the model architecture so that inference could be way faster? So one example is multi-query attention. So Noam Shazir wrote a paper back in 2019. He's way ahead of everyone else, where he said, hey, the bottleneck during inference is that you need to store the KV cache for attention for, all the heads. So what if we only have one head? He calls it one right head. And now I think few models are coming out with multi-query attention now. And I think that's just going to get more and more popular, I assume, this year. Lots of models are going to come out with multi-query attention. We can make inference way faster or use way less memory. So I think as the inference cost relative to training cost, as that ratio is shifting, I think now lots of folks are thinking, when they train model, are thinking about how do we change the model architecture so that inference could be efficient.
For the sparsity work, what is your intuition behind why it is that we can preserve quality if we are like zero out 50% of the entries? Like someone looking in from the outside might be like, that's crazy. That doesn't seem like it should work. I think I have some intuition from theory about why, but I'm curious for yours.
I think these models are over parameterized, so there are more parameters than necessary, and that's helpful for training. You have more paths to explore during training to kind of fit the data. But that means that you're making, let's say, two similar connections that you could have done with one. I'm not sure I have strong intuition there, but my impression is that models learn a lot of kind of redundant features that maybe just help a tiny bit. One extra, two features could be quite similar, but they help just a little bit. So if you collapse them and instead of having only one feature, that could still work pretty well. So that's one intuition. The other intuition is that there could be some kind of adaptive sparsity going on. As in, when you're predicting each token, some tokens are really easy and some tokens are hard. And so maybe intuitively, some tokens, you're not really using the full capacity of the model. And for some tokens, you really do need to use all of the model. We've seen some approach like speculative decoding, which uses like a small model to decode and then a big model to check the result, things like that leverage this intuition. So I think this could be some kind of adaptive computation going on where you don't need all of the model capacity all of the time.
That's interesting. Yeah, I think your point on the models are over parameterized, so you have more paths to explore is interesting. It feels a little bit similar to the LoRa intuition where you can represent some update with a low rank matrix.
Yeah.
That's surprising.
Yeah.
But yeah.
that kind of makes sense. Like, okay, you have to like figure out where the low rank matrix is. So that's why you need these extra parameters. But once you have it, now it's low rank.
Right, right.
And then for modifying the model architecture, aside from multi-query attention, are there other things that you feel excited about in terms of speed ups there?
Yeah, so I think one direction that's a little bit overlooked actually has been more recurrent models. We've seen one or two examples, but the idea is that recurrent models don't need to store the entire history when they do inference. So right now for transformer, for standard attention, you kind of need to store the entire history, called the KV cache, so that when there's a new token that you want to predict, you essentially compare that token to kind of the entire history. Recurrent models instead would compress the history into a fixed state vector. So in the past, I think back in 2014 to 2016, 2017, I think recurrent models were all the rage. So things like LSTM, GRU, and variants. They still had an advantage in terms of inference. Some models being deployed on device, like on phones, they still prefer to use recurrent models like LSTM because they get reasonable quality, but they're much faster at inference. I think for language model, I might be in the minority on this, but I think recurrent models will have something to offer in terms of inference. As we focus more on inference, I think the balance will shift. Recurrent models, I think it's been a little bit difficult to make them work for training. We've seen some examples, for example, RWKV, which is this recurrent model that some folks have trained up to 14 billion parameters that seem to perform on par with transformer. I think that's really promising. And so we need more work to understand what's really going on. Do we really need attention kind of a transformer stack, or can we make do with recurrent connections? And if we can just use recurrent connections that has huge advantages in terms of inference. So that's a little bit more speculative. That's a little bit more on the research side. I would say it's not as proven, but that's a direction I'm excited about.
That's interesting. That is definitely contrarian.
Yeah, I think that's sort of related to some of the more recent work that you've been on, right? Like the Hungry Hippos and Hyena hierarchy and stuff like that, right? So can you kind of walk us through, going a little back in time again, like how did you end up there? Like what was sort of the evolution of that chain of research?
So last year, I spent a bunch of time trying to make attention as fast as possible. So with FlashAttention, so that's now being used in a bunch of places. But as a researcher, I started to look around, hey, what are some of the alternatives? Like how much is attention necessary for, let's say, language model, which is the application that lots of folks care about these days. So we wanted to understand from an academic perspective, when or why do we need attentions? Can we have other alternatives that maybe scale better in terms of sequence length? Because the longer context length has been a big problem for attention for a long time. And we worked on that. We spent tons of time on that. So I looked around and maybe it's a contrarian bet that I want to work on something that maybe scaled better in terms of sequence length, that maybe in 2-3 years would have a shot at not replacing transformer, but augmenting transformer in some settings. There's been approaches like recurrent neural networks. There's been approaches like state space methods that Albert and Curran pioneered in 2021. They came up with this model called S4 that seems to do really well for long range tasks, but has not really worked that well for language models. We want to understand why don't they work well? Can we scale them up? And we made a few modifications to add in more multiplicative interaction and doing more kind of low level work to make them run efficiently on hardware. So we were able to train models up to 2.7 billion parameters. And we saw that they do about as well as transformers. That was really interesting from kind of an academic perspective that, hey, maybe you don't need attention for language model. You don't need a lot of attention. So in our final model, we had 1 or 2 attention layers instead of 20 to 40 attention layers. And that still did pretty well. From an academic perspective, that helped us understand how much do we need attention. And since then, Dan Fu and Michael Polys have been pushing on that direction. So things like long convolution, Hyena, hierarchy, have been pushing on that direction, trying to understand, okay, how much can we replace attention? How much do we need it? They've seen pretty positive results. So I'm bullish on the space, but it's definitely more of a contrarian take.
For the people who are skeptical of this direction, what are their objections?
One objection is that attention works fine for the current models. Like It doesn't take that much time when you scale the model really big, because lots of times we expand on matrix multiplied instead. I think that's definitely valid for the current sequence length that we tend to deal with on the order of, let's say, 2K. When you start increasing the sequence length, which I think for lots of applications, and we're now seeing the context length necessary is on the order of 100K, then attention starts to become unwieldy or becomes a bottleneck again compared to other matrix multiplies. So I think if you just take the setting that exists maybe 1 or 2 years ago, then it seems like attention was fine. It didn't take that much time anyway. We can live with it. But now there are new and emerging applications where long context length is necessary. And so people are definitely thinking about, let's say, how to sparsify attention or how to quantize or collapsing the heads and things like that, how to make that efficient. So there are lots of approaches. So we just took a different path, which is, hey, what if we try other alternatives that could also work quite well? So that would be one objection. I think the other objection's been more, not objection, but it's in people are just following a proven recipe. So the recipe is train a big transformer on lots of data. That has worked really well. So why deviate from that? And I understand that from a production point of view, you don't want to try something that has low chance of working. You want to try something that you're 80 to 90% sure that's going to work, because that's not your focus anyway.
Right.
So I think on the academic side, some folks are thinking about alternative architectures. That's not been the focus for a lot of people. A lot of people are focusing on, let's say, the application. Hey, the big models are here. How can I use these big models to do the thing that I want them to do, rather than tweaking the model architecture and so on?
Right. That makes sense. Yeah. Whereas as a researcher, you want to be doing the opposite.
Yeah. So as researchers, sometimes you have to take these contrarian bets. You could be wrong. Maybe success rate is 20%, but the point is you're making a bet that maybe not that many other people will be pursuing. And 2, you need to kind of adjust quickly. You try it out and see if there are promising results. If so, you keep going. If not, then you can adjust your trajectory a little bit. If you're doing the thing that everyone else is doing, then by default, they're already ahead of you. So that's a little bit harder to kind of make an impact.
I completely agree.
How do you think about the fact that, at least for a lot of the most interesting applications and the things that people are most excited about, they often require these much, much larger models and much more expensive training? And for someone thinking about those people in production, for someone to really want to switch over from that model that they spent a lot of money training to this other way of doing things, even if you do show, for like longer context length is better, how do you think about, needing to train these like much, much larger models and like as part of research? Like even if you show it works a little bit better at the small scale, there's always this question of, does it work if you make it bigger?
Yeah, absolutely. I think that's the question a lot of academics definitely wrestle with. And I think you're right. Nowadays, the bar is much, much higher to show a model that works well. Right? Not only you have to train a big model, you have to fine tune it on instruction, you have to show that it has fast inference and so on. So the bar is much, much higher, simply because I think lots of companies are putting out really awesome product. So people's experience are a lot normalized. Like most people play with ChatGPT. Like they kind of expect that for most models now. So I think that's a question that a lot of academics in this area wrestle with. So I think there are a couple of ways. One is on simplifying and understanding what's going on. So I think that's an advantage that academics can have, which is the luxury of slowing things down and trying to understand things. So for example, for experiment, we might not need to train on large models and lots of data. If we want to isolate a certain behavior of the model, can we make up synthetic data that has the behavior we want? So for example, folks doing experiment on grokking, they were training on synthetic tasks on, I think, modular and arithmetic and so on. Like these are tasks they invented. They want to see if the models can do well on these things. And experiments could take, a couple of hours to run. As long as you still show something that's interesting. I think that's the goal of being an academic. How you translate from, hey, we show something interesting to, hey, we show something that can run in your production. That's a different task. And maybe the right structure is you collaborate with folks in industry. I don't know what the right way is. Definitely there's still people are still trying to figure this out, be it a national GPU cloud for researchers or collaborating with industry. These methods all have different advantages and disadvantages. I think right now we haven't really figured out what is the optimal way. We've seen some really positive results. So lots of folks are now releasing models in the open source that people can play with. And now academics are kind of adapted to that. They can build on top of open source models, fine tune things to do the task they want to do and show interesting results. So I think right now we're in a time where things are moving really quickly. So I don't think there's the right answer. Just like lots of folks are trying to figure out different ways to do interesting things.
Mm-hmm.
You said earlier that kind of thinking about these like recurrent networks, you wanted to use it to augment but not replace transformers. What do you mean by that? Like when you're saying augmenting transformers in some settings, what are you imagining? And kind of how do you imagine it augmenting?
One way is you just have one layer and you would interleave the transformer layer. So the attention layer, the multi-layer perceptron, the RP, and maybe some other layers, a recurrent layer in your network. And maybe that will do something that's interesting. Or you replace some of the attention layers with the recurrent layers. We've seen pretty positive results doing that. I'm hedging a little bit because I know that I think transformers are here to stay, at least for a while. Lots of infrastructure, even on the level of software framework and hardware, are very much tailored to transformers. So I think they're here to stay. So I don't think anything is going to completely replace them very soon. But we'll see new approaches coming out simply because there are now new applications that require either long context or reasoning ability and so on, where of course, current models are amazing and they have a bunch of capabilities already. But there'll be new application areas where some of the model capabilities are missing. And so as researchers, when we think about these things, hey, the model is missing this capability. How do I augment the model to add this new capability? Either adding in layers or replacing some of the layers, or in the case of some of the recurrent models like RWKV, they can replace all of the attention layers with some kind of recurrent layer. So I don't think we quite know what the right way is. So far, my try is that as long as you have a reasonable model design and you have a lot of flops, lots of compute and data that tend to work well. I don't think you have to stick specifically to the current design.
Yeah. That seems right. Like transformers became popular because they scale really well. But like in theory, you could also feed LSTMs a lot more. I think somebody did
a while ago.
Yeah, they were like scaling laws derived for LSTMs. They don't scale quite as well, but it's like unreasonable. Yeah.
Yeah, they still scale. They get better as you throw more compute at them. I think we did some experiment where we keep the transformer kind of macro architecture, but we only replace some of the attention layers with recurrent layers, and that can still work pretty well. So you don't have to replace all of the layers with LSTM. We can replace some of the layers with LSTM. It was more of a fun experiment that we didn't really write up, where we replace some of the attention layers with either LSTM or some recurrent layers, and that can work reasonably well. It trains slower though, because the hardware and the framework are so optimized for attention. But that was a fun result.
Are there any benefits, did you see, to that?
I'm not sure there's any benefits. It was like more of a curiosity thing. Like, hey, what if I swap this thing in? Yeah.
Okay. Does it still work? The answer is yes. That's cool. Yeah. That's really interesting. So we've been talking about recurrent stuff. Let's talk about FlashAttention. Like, how did you decide to work on FlashAttention? Where did the ideas come from? And then how did you get the results that you did?
Right. This started early last year. And previously, I've worked on attention approximation as well. So the goal there is we've been interested for a few years of scaling to longer context length for different applications, be it the medical time series or medical imaging or audio, where the context length is much, much longer than current transformers can handle. Mm-hmm. And so we wanted to push in that direction. And we saw that one of the bottlenecks is in the attention layer. And we've worked on attention approximation in the past, and we show some pretty interesting results. But when we talk to practitioners who actually train language models, they say, well, we don't really use these attention approximation methods. One, they lose in terms of quality. So because you're approximating attention, the quality of the model is a little bit worse. But two, what's really interesting, they say, well, even though they do fewer flops, fewer floating point operations, they are not really faster in terms of walkout time. Oftentimes they are slower. So this was, again, kind of the same theme coming back, which is when we design algorithms that we didn't really think about the hardware. In practice, people don't really like to use these things because they're just slower, right? So that really motivated us to figure out, can we design some attention algorithm that can scale to longer sequences, yet still remain hardware efficient. That's something that lots of folks have been working on for the past years or so, ever since transformers got popular.
Mm-hmm.
And so there was just around the time when I started getting really interested in machine learning performance, like speed. And so my advisor, Chris, he said, well, if you're interested in speed, why don't you take a look at MLPerf? MLPerf is this industry benchmark for machine learning performance. One benchmark is MLPerf training, which a bunch of companies will benchmark their infrastructure, their implementation to show, hey, we can train this model to this quality in this amount of time. It's a really competitive benchmark. Lots of companies invest lots of resources there to show that, hey, let's say our GPUs are better than such and such, or our framework is better than this other framework, and so on. So there's a lot of kind of financial incentive to do well in these benchmarks. So Chris told me, hey, why don't you take a look at MLPerf? Like, these people really know what they're talking about when it comes to machine learning performance. And I dig a little bit deeper into MLPerf, and I looked at one of the implementation of BERT from NVIDIA. So it was written by this guy, Yang Chen. I was blown away. I studied that for, I think, 2 weeks. I sent him an email. I said, wow, your attention implementation is awesome. I learned so much, which is like a friendly email. And of course, he's happy. But one side effect of MLPerf was that the implementations are quite tailored to the benchmark. So if the benchmark is BERT, then the implementation essentially only works for BERT, in the sense that it works for A100 because that's the GPU they use for the benchmark. It works for sequence length 512 and not any longer because that's the sequence length that the benchmark can focus on. It works for shorter than up to 512. So there was like no reason to go above 512 and so on. It works for like, head dimension 64 because that's what BERT is. And so it's a really tailored implementation to BERT, but I was blown away at all of the low level implementation that was going on. I knew that I wanted to make it scale to much longer sequence lengths. I started formulating some ideas of, hey, we can decompose the attention for long sequence length into attention for short sequence length in this particular way. It's a pretty old trick from the machine learning literature. I think the NVIDIA folks wrote about it in 2018. I think it's called Online Softmax or something like that. There's a Google paper end of 2021 by Rabe and others on using that trick to kind of decompose long attention into attention with shorter sequences. And I knew that trick exists, and I wanted to. So I sent an email to this guy, Yang Chen, and I said, hey, I think we can make your implementation work in this particular way if we use this trick and so on. And he said, oh, I think we tried to go longer, but we ran into this difficulty and so on and so forth. So we exchanged a couple of emails. After a while, I decided, like, hey, I believe in this direction. I'm just going to go do it. And so that took me, I think, 2-3 months of just coding in CUDA. So that wasn't the most pleasant experience, but in the end, we have something pretty nice. It was slow going. Like, CUDA it's a low level language. It's not as pleasant to work with compared to Python or PyTorch, but I believe in the direction. So I was willing to spend 2-3 months just doing that. And with the help from Dan Fu as well, he's a PhD student in working with Chris Ray, we finally have something that was pretty nice. We show that, hey, you can do attention much faster, much more memory efficient, and then scale to much longer context. Essentially, the idea is, hey, we take something that the system folks have been thinking about, things like kernel fusion. We take something that the machine learning folks have been thinking about, like softmax decomposition and so on. And we can combine some of these ideas with a careful implementation. Like, we show, hey, you can actually make this work. And we got something like 2 to 4x speed up compared to kind of the best implementation out there. And the memory scaling is linear instead of quadratic in the sequence length. So we put that out. We spent a bunch of effort improving the implementation as well. So I think this is now part of PyTorch 2.0. So I think lots of folks are using that now to train their models.
That's awesome. That's really exciting.
There's a tweet that I love about this. I mean, basically the person said, this is going to save the community like tens of millions of dollars, if not hundreds. And if there were an Oscar for AI, this team deserves it. The paper is a tour de force in technical chops and an object of beauty. I think that's maybe about right.
Yeah, it is really.
Thank you.
I'm curious, did you try ideas that didn't work? Like you said, you ended up taking kernel fusion and softmax decomposition. Did you try other stuff and you're like, can't make this work?
Yeah, so I think I wanted to combine some of the sparsity idea with this. So for sparsity, there's usually two classes of sparsity. One is static sparsity, which means you know beforehand that you want some of these entries to be zero. And dynamic sparsity says that, hey, you're going to change the locations of the non-zero from time to time. And generally, the pruning community have found that dynamic sparsity is better quality-wise. But in our experience, static sparsity is just a lot easier to work with. And in terms of speed, they're easier to implement. You generally can get speed up with static sparsity. I've been wanting to make a dynamic sparse attention work for a while. I haven't really been able to do so. Dynamic sparse attention would be like, given the queries and the keys, can we then predict where the zeros are going to be? And that location is going to change from one iteration to the next. And then can you dynamically adapt your implementation to deal with this kind of dynamic sparsity? We haven't been able to make it work. I think it requires quite a bit of effort and maybe deeper thinking. We found static sparsity to work pretty well. Again, block sparsity seems to be pretty hardware friendly, and we show that we can combine FlashAttention with block sparsity, and that gets you linear speed up in terms of the density. So if you only have, let's say, 50% of the blocks being non-zero, then you would get 2x speed up. That's really cool because for sparsity, you rarely get this kind of linear speed up. Usually the parity is, you hit parity when you're about 10% non-zeros or something. So if you have 90% zeros, 10% non-zero, then you start to be as fast as a dense implementation. But in this case, we show, because of blocks structure, we show that even if you only have 50% non-zero and 50% zero, you can get 2x speed up. So yeah, so we've been wanting to make a dynamic sparsity work. We haven't been able to do so. I hope someone will do it. From a machine learning perspective, I think dynamic sparsity makes sense. From a systems perspective, that's been hard. So I hope someone will do that soon.
Yeah. On the static sparsity, that's not part of the existing open, released FlashAttention, is it? Or is it already part of that?
So it is part of that. It is more of a proof of concept. We show in the paper, hey, we can do this. Here's an implementation. I haven't had as much time to kind of polish that implementation compared to the dense attention implementation. I've been wanting to work on sparse attention again for a while. I just haven't had the bandwidth to do so.
Mm-hmm. Did you do any experiments with kind of the performance in terms of downstream evals that you see from various levels of sparsity when doing sparse attention like this? Clearly, if you have if you're only dropping 5% or whatever, it probably doesn't make a difference at all. But of course, you're not getting any speed up. And if you're dropping 99%, well, that's probably not going to work super well anymore. So
right.
What does that curve look like?
Yeah, I don't think we have numbers for language models. We did try for this more toy task called PathX, which is this more synthetic task where you can given an image and there's a bunch of lines and there are dots and you're supposed to classify where the dots are connected. And it's supposed to push transformer to the limit in terms of context length, because the context length is either 16K or 64K. And so existing models either just don't run, or because they do approximation, they don't do better than random. So with block sparsity, saw that we can get context length we could run something reasonable with context length 64K, and it was able to do kind of the first model that can do better than random on this synthetic task. I would love to go back and explore sparsity again for language models, especially for long context.
Seems promising, especially at mild levels of sparsity. Generally, at least the things that and the sparsity levels are pretty mild. You're getting a linear here.
Right.
You usually don't lose much for just a little bit of sparsity. So helpful.
Yeah, I think there's probably a right trade-off. Maybe 50-50, I don't know exactly, but there's probably a nice trade-off in terms of speed and quality there.
I wonder, could you do something adaptive over time, sort of like the Monarch matrices also, in slowly ramping that up over time if you wanted?
Yeah, that sounds like a good idea. I think the pruning community has been writing lots of papers on what is the right schedule for sparsity. You can increase or decrease sparsity either at the beginning or at the end. I think lots of work has been going on there. My understanding is they have focused quite a bit more on computer vision models. And so we'll see how well they work in terms of in language models. But yeah, I think that's a very sensible idea. I think having the right sparsity schedule could get you, 90-something% of the quality, and maybe there's some nice speed up to be had there. I think that direction is pretty promising.
Especially, I don't know, you could be pretty clever with it over time in terms of how the things are interleaved and how they shift over time, but keeping it static, just paying attention to a lot less over time and like slowly learning things that are one and fill it in later and like get all the detail really needed, I guess.
Yeah. So far, we've been focusing on more just simpler approaches. We just want to do, hey, what if we do this dumb thing of just do static sparsity? How well does it work? Like can we understand the limits of just using static sparsity? And then, okay, once we understood that, then maybe like, hey, like how much dynamic sparsity do we need to add? And so on. So yeah, lots of work to be done.
Yeah, the dynamic sparsity also seems super interesting, or the adaptive sparsity also seems super, super interesting in terms of really need to be paying attention to, you actually shouldn't be paying attention to most of these tokens most of the time. Like in a sense, you almost should, I would hope, get a better result by doing this in the right way, right? You really shouldn't be attending to like nonsense or unrelated words there to like skew the things that you see.
That's juicy.
It does seem like I can understand why this is done yet. A tricky thing there is how do you actually make this work in terms of deciding like which things to turn on or off? Right? Like being so binary, I feel is like happy for gradients.
Right. Yeah. I think there are a lot of clever approaches to kind of figure out the sparsity math. One approach is called locality sensitive hashing, which is this technique that, let's say, given a bunch of queries and a bunch of keys, can we essentially cluster them together so that the similar keys in the queries will be kind of in the same bucket. So essentially it's clustering. And so once we figure out that, hey, there are a bunch of keys and queries that are similar, then we only need to compute attention within the same kind of bucket. So there are approaches like hashing and clustering. Some folks have tried. They show some positive results in some settings. So it remains to be seen if these things can actually work at large scale for the task that maybe a lot of people care about right now, like language modeling.
And then, as you pointed out many times and are totally right about, like getting us to work and actually be faster in practice is also really an important piece of this, even if this does sort of like theoretically work really useful, runs 4 times as slow.
Right. Yeah. I think there are different stages of these ideas, right? It could be like, hey, someone has an idea, they show that it works in theory, but there are limitations. And then someone follow up would say, hey, we address this limitation this particular way. I don't think you have to go all the way saying like, hey, here's a production ready thing. Of course, if you can get there, it's awesome, but it's usually work building on top of each other.
Yeah. So I guess, has anyone even shown if you do that sort of paying attention to only some of the keys, does that work just as well?
I think in some setting that works well, but I don't know if the result in like just language models.
I haven't seen, of a paper that I'd be curious to check it out. I haven't seen one that does that exactly, but it does make sense. Yeah. Why should you bother computing all this attention for the stuff that doesn't really matter because it's all soft-maxed and product anyway. So what are you doing with all those floating point ops? Interesting. Well, there's certainly, even though FlashAttention is already a really cool achievement, you're right, there's like a ton of other really cool stuff to be built on top of it.
Yes. I was curious, what are you optimistic about in terms of iterating on FlashAttention, people iterating on it? Do you feel they are, especially, it's definitely not promising.
Right. Yeah, so I think there are a bunch of directions that I'm pretty excited about. So some of these are on the system side, some of these are on the machine learning side. So on the system side, I think there's a lot of work to be done to kind of have an entire stack that's really efficient. So the stack going from software frameworks like PyTorch to compilers. So for example, the OpenAI folks, Phil Tillett has this compiler called Triton that can make a bunch of things much faster, and down to the hardware. So this is a kind of a longer term trend that we'll see more integration across the stack, because right now the limitation for a lot of approaches is that it's really hard to get an efficient implementation of a new idea. So if you use just using transformer, standard transformer for your task, it works really well, is well supported from both the software framework, the compiler, and the hardware. But let's say you have a new modeling idea that's tailored to your application, or you want to augment some kind of capabilities for the models. If you want to change the architecture, for most people, it's quite difficult to go lower level and can figure out what is the right the most hardware efficient way to do these things. And I think that's where things like software frameworks and compilers would come in. So I think that the PyTorch folks have done an amazing job with PyTorch 2.0, where they can now capture the graph. You still write your code in PyTorch. They can capture the graph. They can generate efficient code in, let's say, Triton. And then the Triton compiler would then generate like low-level code that runs on GPUs or other kinds of devices. We'll see more of this integration. So that direction I'm pretty excited about. So I've been talking to folks from the PyTorch team and the Triton team. I've been wanting to work more on FlashAttention, kind of the next version of that. So I think there's still more things to be done there. I think we can still make things quite a bit faster still. It was already 2 to 4x faster than other baselines when we released that last year, but I think there's still a little bit of headroom. Like we can make that faster still. And especially nowadays where long context, since lots of models are being trained with long context, I think that's important to get attention as efficient as possible. That's on the system side. On the machine learning side, I think there's still a lot to be done on the augmenting model capabilities, especially for long context. So as I mentioned, I'm bullish on some of the architectures that are different, a little bit different from Transformer. And maybe for long context applications, these architectures could prove to be better or like more efficient. And I think with more use cases that are emerging, so people now want to use like, plugins with ChatGPT. People want to do web browsing. We all want these things to use tools, or these things, they have a bunch of agents talking to each other. Chatbot, where you want the chatbot to remember your history, personalization, and things like that. I think there's a lot of use cases for long context now. And so there's more opportunity for other architectures that may be well suited to long context. So that's another area that I'm excited about.
That's really interesting. I feel like our unusual or controversial opinion that this whole thing about recurrence is one.
Yeah. Are there any other ones?
Are there any others that feel like other people don't agree or?
Yeah. So I would say, I think there are many paths to a high performing language models. So right now there's a proven strategy. People follow that. I think that doesn't have to necessarily be the only path. I think my prior is that as long as your model architecture is reasonable and is hardware efficient and you have lots of compute and you have lots of data, the model would just do well. This remains to be validated and so on. I think folks are now just following the kind of proven strategy, and that makes sense. But I think in the future, we'll see maybe more model diversity cater to different needs rather than this one architecture that everyone is using. Again, that has certain advantages. You want a unified code base. You want something simple that works across different domains. Transformer has been amazing at that. And from an industry point of view, like that's great. You want your implementation to be about 200 lines of code and it works everywhere. That's great. But from a kind of academic research point of view, I think there are many paths to a high performing language model.
Mm-hmm. And we were told 20 years in particular being a whole range of architectures, whole language models, maybe they have trade-offs from each other and maybe are used in some are used in others, as opposed to like a simplified one.
I think there's going to be some kind of decoupling where you have a really strong base model that could be Transformer or otherwise, and then you have a lot of kind of hooks into the model that either does personalization or reasoning, or like essentially I'm imagining kind of a floppy disk analogy where you have your computer and let's say you want to do this particular kind of reasoning, then you insert this kind of floppy disk. Or if you want to personalize to the coding style of this particular developer, you slot in this floppy disk. We've seen some of that already, which is the trend is having a really strong pre-trained model. And then some of the capabilities or theorability come from the post-training. I don't know how we're going to get there yet, but it'll be exciting.
Yeah, I think that's interesting. Like Laura is one example of like,
yeah.
Now you can like apply this little fine tuning. And then you can apply multiple fine tuning. Unique aspects.
Yeah.
You can use like applying it onto matrix transforms. So you can see why you would be able to apply them like this. But yeah, I think it's very interesting. Do you have any other unusual controversial?
Maybe in the short term, I think there's going to be a lot more focus on inference as these models are being deployed. I think these models provide lots of values now, either personal use cases for entertainment or for business use cases. So I think there's going to be a shift towards focusing a lot on inference. How can we make inference as efficient as possible from either model design or software framework or even hardware? So we've seen some of the hardware design that will cater to inference now. So I think, for example, Google CPU has a version for inference and has a different version for training where they have a different number of flops and memory bandwidth and so on. So even phones are going to be more tailored towards doing inference. I think Apple has put in, for example, neural engines on the iPhones to be able to do model inference already, and we're going to see more of that. And so when it comes to model design, I think people are going to think more about inference. People are going to think about, for example, inference could also mean like personalization. So if you're a chatbot, you want to be able to take in really long context. So how do you design a model that can take in really long context for, let's say, chatbot? So I think in the next year or so, a lot of focus will be on how to make inference as fast as possible.
How much efficiency do you think? 10x, x, 30?
Well, it also matters what you're asking.
It does matter.
Are we going to get latency, energy, throughput? Like, what exactly are we talking about? Yeah.
Right. Yeah, I think right now, if you're doing single batch inference, where let's say you're running on a local GPU and you're dealing with a chatbot that you only have one user, then I think you're saturating the memory bandwidth because you're loading the weights in and to do computation. You're not using a lot of the flops. I think the flop util is on the order of like a couple %, right? And that's why batching is important, because if you run an inference server, you want to batch, 32 queries at the same time to kind of get that efficiency. So that means that for certain use cases like single batch inference, there's still quite a lot to be gained there. And there's going to be hardware that's more designed for inference. We've seen some of that already. I expect to see more in the future.
That's true. Do you feel like you have any opinions that you once held strongly, but now you reversed your position?
I used to focus a lot more on the mathematically interesting aspect of the project, and I still like that a lot. And I used to think that, hey, as long as we prove something that works, like making it work in practice is maybe someone else's problem. Like someone else will come and make that work. Like I've shown that it works, I've proved that it works in theory. Now someone just have to make that work in practice. And coming from my background in math, that was a natural belief. But as I get exposed to a lot of ways to use these models, practitioners who have different concerns, I realized that it's much more effective to actually talk to practitioners, and they will give you the kind of feedback that will really push you forward. Like they will say, hey, it works for us in this case, it doesn't work in this other case. And that's the kind of feedback that you don't usually get. I think that feedback is really, really important. So, for example, I've been very fortunate to be in a lab where the folks work in different application areas, like audio processing, medical imaging, medical time series, and so on. And talking to those folks working in application is great because they really do care about their application. I think for some machine learning researchers, they try it out on one domain and it doesn't work here. Let's try it with a different domain and maybe it'll work there. That's fine. Like on the method side, we want to develop methods that maybe work on some domains. But when we talk to practitioners, and they really do care about, let's say we have folks who really care about seizure detection from EEG signals. If it doesn't work for their application, they will tell you that feedback. Right? And having that direct feedback is really useful because it forces us to confront with the limitation of our method. So nowadays, I think my belief is that we should engage much more with practitioners, and because they give us the right kind of feedback to get better in terms of developing our methods.
Given that, personally, how are you thinking about it? Like, are you going more industry route? Are you going to stay in academia?
I'm planning to be in academia, so I'm going to be an assistant professor at Princeton starting next year.
That's really
Thanks. But in the meantime, I'm looking to explore some options of either an industry or a startup. So I haven't decided yet. I'm still talking to folks. But yeah, right now it's a really fun time to be in industry and startup. There's so much happening. So I'm pretty excited about that. Ultimately, I really do like research. I really do like mentoring. So I think long-term academia is kind of the right choice for me.
Do you feel like, thinking about the future, are there any concepts you could be more widely known?
machine learning researchers don't get exposed to as many areas as they should be. So one reason is that because there's already a lot going on within machine learning and it's hard to keep up. The other reason seems to be the other fields don't seem to be as immediately useful to the kind of research that we do. But ultimately, I think as a researcher, you have to constantly learn new things. Otherwise, you keep doing kind of the same thing over and over, and you might not be as relevant. So for example, I started reading stuff from like numerical linear algebra books that seem to have nothing to do with machine learning. That's how a lot of my ideas started, because we were thinking about how to do linear algebra, which is matrix operations, in a numerically stable way, in a way that's efficient, and so on. That has really benefited by my thinking. For example, my close friend Albert Gu, who's been developing a lot of these state space methods, the inspiration comes from things like signal processing. The roots go back to Kalman filter back in the 60s, and he's been trying to use some of the ideas and apply it in a deep learning setting. So I think that's where new ideas could come from, which is signal processing, numerical linear algebra, even databases, theory, and so on. I think they have a lot of interesting ideas that maybe don't seem immediately applicable to the machine learning research that we do. But I think over time, you have to keep learning new things and trying things out. Like that's kind of the luxury of academic research, is that you get to constantly try new things and try to apply them.
Do you have any intuition? I'm going to read more books on this area or papers in this area. Are there particular areas that you feel would yield fruit at the moment?
I'm not sure they would yield fruit. There are lots of things I'd like to read, like a lot of them more on the mathematical side. Again, given my background. So for example, for a while, I really enjoyed reading about concentration inequalities, which is this area that's useful to prove concentration bounds and it's useful for statistical learning theory. I'm not sure how relevant that is to my current work, but that has been just very satisfying. So it's something I think you just kind of have to block time, and you say, hey, every week I'm going to spend however many hours kind of reading new stuff that's not related to the work that I do every day. So that's what I enjoy. I think otherwise you get too caught up with all the current trend, and because there's so much going on, it's kind of hard to get new ideas if you only focusing on what's current and what's popular right now.
Yeah, I totally agree.
Any tips or tricks for other people that are kind of getting into research? Like like one is, make sure you set aside time to learn new things. Other things like that, like things that you learned or
pragmatic.
Or very pragmatic ones.
When training networks.
Yeah.
Things like that. Make good eval.
Yeah. So one thing I found has been enormously helpful is getting better at engineering. So this is somewhat overlooked if you're a machine learning researcher, such maybe in some PhD programs, where the focus is just a lot more on or writing papers and so on. But I think getting good at engineering has been kind of an amplifier. So you can try out ideas faster. There are lots of ideas. People will have lots of ideas. It's like, how fast can you try them out? How fast can you execute and get? It's about the process of doing research. And part of that is being good at engineering. Like, given an idea, how fast can you implement it correctly and kick off model training and come back later and see whether it works or not? Do you have like a code base that you can try out ideas easily? And how that translates to research is, let's say you read a new paper and you're interested in it. Can you implement that and test it out? Because reading a paper is one thing, but like trying it out is another level of like understanding how things work. Like actually implementing things has been enormously helpful. One of my friends, Phil Wang, his GitHub name is Lucid Rains. Anytime a paper comes out, the next morning he has a GitHub repo implementing that, right? And of course he's fantastic. You don't have to get all the way there, but I think getting good at engineering is actually really, really helpful for machine learning research nowadays, especially in this area where a lot of the breakthroughs are more driven by empirical results.
Very cool.
Yes. So engineering is an integral part of that. And maybe there's not enough focus in engineering in a lot of programs.
Yeah. Yeah. We get a lot of people applying research scientists. What's the difference between this role and research engineering? It seems like it would be very different. And I'm like, honestly, team, I truly cannot tell the difference. Like all the engineering all the time.
100%, but it's largely that.
95%.
Yeah, totally.
Are there any unpublished results or like research failures that you've had where you're like, man, this really should have worked, but it didn't? Anything like that comes to mind?
I've been working on follow-up on FlashAttention. The original implementation in terms of utilization is already quite a bit faster than the baselines. But when you actually measure the utilization of the device, it's actually not as high as you would expect. It's like on the order of maybe 30% util. And if you have a well-written like matrix multiply implementation, you can get to 80 to 90% utilization of the device. And so there's still quite a bit of a gap, right? Yeah, I think when we wrote the paper, we explained, hey, here are the bottlenecks. Here's how we address the bottleneck. But I don't think we went all the way to like making sure it's as efficient as possible. So there's probably, it's because maybe we really don't understand all of the details of the hardware. So there's still some overhead that we're missing or some of the bottlenecks that we're missing. And yeah, I think for FlashAttention, I would have expected it to get closer to much higher utilization, but right now it is not as high as I would have liked. So that just says that, hey, there's still some headroom that we can work on. And I plan to go back, and now that I understand the hardware a little bit better, I plan to go back and improve that implementation.
That's exciting. I can't wait.
Yeah, I'm excited to see that.
Yeah.
Yeah.
Awesome. Thank you so much for being on the podcast.
Yeah, this has been really fun.
Thanks for listening to the Generally Intelligent podcast. If you like this, please consider giving us a rating and leaving a review on Apple Podcast. On Twitter, I'm @Kanjun, Kanjun, and our lab is @GenIntelligent. Until next time.